Okay, good. So, this is the second to the last unit that we have.
So what's the last one?
That's like quantum mechanics.
Sorrow.
Pain, yeah. Okay,
Something more black.
so you all obviously had experience with magnets, okay? It's not anything new. The math is what gets weird, and then how it ties in with, oddly enough, circuits and electricity. So you always study electricity first before you study magnetic theory, because what they figured out, thanks to Michael Faraday, is that electrical fields produce a magnetic field around it, which I'll show you in just a second. So this is why it's called electromagnetic theory, because your electricity, when you have a moving field, creates a magnetic field. But then if you reverse that, and you can also say, well, if I have a changing magnetic field, that can create an electric current. So the door can swing both ways. So you all probably already understand a little bit about magnets. So if you have a magnet, what do you always have in terms of poles? The north and the south pole. Now, this is even gets a little bit wonky. So you have a north pole and you have a south pole. So if you look inside the Earth, all right, and I happen to have a little model of an Earth, okay?
Not to scale.
One of the most important things that allows us to be here having this conversation is that inside the Earth, there is a magnet, okay? Now, the beauty of that and the importance of that magnet is that that creates a magnetic field around us. So that magnetic field acts as a shield. So space is absolutely horrible. There's so many people like, oh, space is so cool. Space will kill you, okay? That's it. There are any number of things in space that will absolutely kill you. It's a vacuum. It's cold. You're being bombarded with high energy particles that will jack up your DNA, okay? Space is not pleasant, okay? The only thing that allows us to basically exist is that if this was the Earth and you slice this in half, the edge of that tennis ball is the atmosphere that allows us to live. That's it. That's gone, we're screwed. So on scale, the thickness of this tennis ball is what allows us to exist on this rock. So one of the things that allows us to have this atmosphere is this magnetic field. Because what the magnetic field does is that the sun is ejecting all of these high energy particles. Even I think it was last fall, usually with the northern lights, and there's also the southern lights, we just talk about the southern lights because we can't see them because we're in the northern hemisphere. But the southern lights or the northern lights are created by these particles. When they come in and they interact with this magnetic field, they get diverted to the poles. So those high energy particles, instead of bombarding us, that magnetic field shields us from that, and then they only end up being diverted to the poles. So the cool thing about the magnetic poles is that they've actually figured out that the magnetic poles have actually switched throughout history, and how they figured that out, it's pretty cool science. So have you all studied continental drift?
Yes.
Okay, know what I'm talking about. So here is North America, and here is Europe. So in the middle of that, there's something called Mid-Atlantic Oceanic Ridge. And they found this in World War II when they mapped the ocean floors using submarines, because they had to know, hey, how deep or shallow is the oceans, so that we can have a good map when the submarines are traversing through the oceans. And so what they found is that, and this traces all around, so the Earth somewhat, if you look at these ridges, is like seams on a baseball. So what they figured out is a couple of things, and this is where this became like a puzzle. First and foremost, the first kind of piece of the puzzle is that if you look at the eastern coast of South America and the western coast of Africa, they fit together like a puzzle. And it's like, that's interesting. Like literally, if you push this back together, it's like, oh, those fit together. Then they figured out running down this gap is the mid-oceanic ridge. So then, once we developed the technology, they started taking core samples from the ocean floor on either side of the mid-oceanic ridge. And what they found is the material that was closest to the mid-oceanic ridge was young. And the farther out you got, the older the sediment was. So it's like, because they had the idea that the continents could move, they just didn't have a mechanism. It's like, well, that's just weird, because even when this was first proposed, which is relatively new, this was theory of like continental drift was proposed like in the 50s and 60s, and initially it was like completely, like not even taken seriously. Because it's like everybody goes, there is no way you can make an entire continent drift. Can't happen. But, because they didn't think that there could be a mechanism. So what happened is that this kind of became an interesting piece of the puzzle that fit together. So they started figuring out the ages of the sediment. The farther you got from the ridge, and it was symmetrical on both sides, the farther you got from the mid-Atlantic ridge, the older the sediment got, and it was symmetrical on both sides. The other thing that they did is that when magma that contains iron, when it cools, it lines itself with whatever magnetic field of the Earth is. So when this magma comes out, it's hot, the iron particles are bouncing around, well, we know. But then when it solidifies, those iron domains, these magnetic domains, line up with the magnetic field of the Earth. So a very, very crude way, very, very crude, I emphasize crude way to make a magnet, is that if you take a piece of metal and you get it red hot, and this is what blacksmiths used to do, they would take an anvil and they would get it red hot and they would put it on an anvil, and they would line it up north-south. And what they would do, they would get it red hot, and then they would put that metal on the anvil, and then they'd start to smash it with a hammer. And so that red hot metal, because it could move around because it was hot, and then by the act of hitting it with the hammer, it would force those magnetic domains to line up with the magnetic field of the Earth. So in the old days, it wasn't very good because it wasn't a very strong magnet. But what that did is that reinforced the idea. It's like, oh, great, hey, there's something going on here. And so they found when they did that, it's like, how did this ever begin to happen? And it's because the particles would line up with the magnetic field of the Earth. So when they began to analyze and figure out that, wow, we could look at these core samples and figure out the direction of the magnetic field of the Earth, what they found is that every once in a while, and this isn't like weekly, thank God, okay? But I think it remembers about every 10,000 years, they would find out that the magnetic field of the Earth would either completely shut off for a while, or it would switch. And the North Pole was the South Pole, and the South Pole was the North Pole, okay? Bad thing is we're about due for that to switch here probably within the next, I don't know, give or take 2,000 or 3,000 years. Don't worry about it. It isn't like we have the exact time, 5 minutes. Okay, here we go. Magnetic field's going to switch. But that's happened, and they can. And here's the cool thing about it, is that when you looked at the samples on each side, it completely matched in terms of the changing of the magnetic field. So what this did is that it allowed an explanation to figure out why Europe and North America are being pushed apart. So they changed the model of the Earth and said, okay, these continents are like basically floating on like a layer of magma. And so as that magma comes up through that mid-oceanic ridge, it records the magnetic field and it records the relative age. So as this is being formed in the middle and is pushing this apart, it's like a record, and it's recording what's happening to the magnetic field, and then we can work backwards and find the relative age of these. Okay, so I'm going to pass this around. Got a couple of cool toys. So this is a model of the Earth, and inside here there's a magnet. So this is an external magnet. So what you can do is take this and hold it like this, and then as you move around, you'll see that the magnet flips, and then the blue end comes down like that, and then you can move it around like that, and on both sides. So even if you go way out here like this, you'll see that change and go around. Now, let's think about this. Do you think there's a direct or inverse relationship between the strength of the magnetic field and distance? Inverse, right? Closer you are, smaller the distance, the greater the strength of the magnetic field. So that's just kind of cool because you can sit here and go like this, boom, and you'll see it completely flip around as it goes. So take that, pass that around. Okay? Now, the other thing you've got, and we've played with this before, this is known as ferrofluid. And so you got this is a pretty strong magnet. So when you do this, and this also kind of reinforces this idea that magnetic fields aren't a smooth continuum. Gravitational fields are a smooth continuum. It isn't like, there's lines of greater magnetic gravitational strength. Thank God gravity is pretty strong. It's like you're walking along and all of a sudden, boom, so if you notice, this turns into like a spike, like this, okay? So if the gravitational field existed in field lines like this, it would be weird, because you'd walk along and all of a sudden, bam, gravity got really strong, like, oh man, hit one of the gravity field lines, okay? And then you'd walk a little bit farther, and then it would get weaker, and then it would get stronger, and then it would get weaker. Go on, are you having fun?
Yes.
Okay. It is pretty cool, I'm not gonna lie, that's a cool. Or you can do what Cohen did and keep the magnet stationary and move the Earth around it. That's another option. I'm just saying. So, now the cool thing about this is that, number one, it's a phenomenal demonstration to show the inverse relationship between distance and the strength of the magnetic field. And it also shows, because it gets, this is a highly non-technical term, but because it gets spiky and not as a smooth continuum, it also shows us the magnetic field isn't just one continuum like gravity is. It exists within very specific field lines, and then if you move it away, then you'll see that those spikes become less pronounced because the magnetic field is getting weaker. Now, so if you do it with like the flat side up, you get one set of magnetic fields. But if you turn it, and if you go to and you put the ends on it like this, you get a completely different look. And if you kind of rotate it, you'll see that as that spins, you can completely change the orientation of the little spiky things. So, pass that around. All right. Now, here's going to be one of the weirder things I'm going to tell you today. Uh-oh.
Magnetism. Magnetic fields have mass. I'm going to calculate the velocity of the magnetic field.
It's extra weird gravity. It's not difficult. Well, I mean,
Confederate?
electro.
It'll make sense in just a second.
Traitor. The traitors.
We're failing this test, bro.
Yeah, but yeah, it's just extra weird gravity. Unlike the normal weird gravity that is electrical shenanigans. No, this is just extra weird.
It's the newest thing.
Oh god, I hate that unit. I keep opening it to this page.
Yeah. With continuous thing.
Okay, now,
You need to make some new ferrofluid.
That's really sad.
this is where this is gonna get weird. Just accept it, okay? It just is, just
That's
accept it.
the
Don't fight it, just go with it.
Magnet piece.
So, if you look at how a magnet works in the Earth's magnetic field, okay? So, one of the things you have to define is what's the direction of the magnetic field. So this is what I've, over the years, I just called it the Confederate definition of magnetic field. So the direction of the magnetic field, and this is going to be hugely important later on, is the fact that a magnetic field direction is either, you have one of two options. It's either going to go from the south to the north, or it's going to go from the north to the south. So I call it the Confederate definition. So the magnetic field, the direction of that field, and now we know that it exists in spikes, because that's how you can tell, right? Okay, look at the ferrofluid, you get spiky stuff. So the direction of this is going to be going from the north to the south. So if you have a simple bar magnet, you have a north pole, you have a south pole. So these field lines emanate from the North Pole, and they end up going in at the south. So north to south. That's why I call it the Confederate definition, heading towards the south. Now, what do you know about poles on a magnet? What makes them attract or repel? They're opposite of each other. Now, here's where this gets weird. Here's the Earth, right? If you have a magnet on our Earth, which you do, which end of the magnet points towards the North Pole of the Earth?
South. Southern pole.
No, the North Pole of the magnet in the field points towards the North Pole.
That's why it's called the
Okay?
What?
But, the magnet inside the Earth, which end of that magnet is actually at the North Pole?
South.
South.
The south end,
That's why we hate physics.
That's why the North Pole points towards the
I feel
north.
like the definition
Yes.
of a magnet should just change depending on what it is in the
well, wait, if it happens in your lifetime, then you can say, hey,
You know what?
it's just.
Back in my day,
Back in my day, North meant North, okay? Damn it.
Apparently north
Obviously
meant
it did.
south.
Yeah.
North meant south.
So,
Yeah.
here's the weird thing about this big magnet inside of our Earth, is that what we consider the North Pole is actually the South Pole. Okay? That's why I said it gets a little bit weird. Okay?
Say that again.
I'm just telling
Say
lies.
that again.
you. What?
The last thing you said.
So, inside the Earth,
That's
Yeah.
why we call
Okay.
it. Yeah, you're right.
what we consider to be the North Pole is actually the South Pole of the magnet inside the Earth. Now, so which direction do the field lines go around the Earth?
The
So,
opposite way.
that goes from the north to the south, right? So the magnetic field lines emanate from the north and they come into the south. So this is why you have the highest intensity on the north and south poles. This is why you get the northern and southern lights at those regions. If it got really weird, the magnet would be along the equator,
Which doesn't make much sense.
which would be really weird, because then instead of having northern and southern lights, you would have equatorial lights.
Be unstable.
Oh, yeah, it'd be cool for us because we get to see them a lot more. So, I think it was last fall, the Northern Lights actually made it down to Kansas. Did anybody actually go out and see them?
Yeah.
I think it was last fall. It was cool because, yeah, you kind of had to have your camera on your phone to really see it. But, so what happened is that we had such intense, highly charged particles from the sun that interacted with that field that normally it dies out. But because there was such intensity, that energy got farther south and we were able to see it. Okay, Danny, stop you on the camera. Let's go to the back.